Good morning, everybody.
Hi, good morning. Nice to see you. Bye-bye.
Good morning, Garrett.
I think we can wait a few minutes, a couple of minutes, to have some other participants.
Sure. I know Jesus said he was joining us this morning as well, and as I said, our main speaker is a little late. He said he would join at about 10 minutes after. So Dr. Santilli, thank you for the emails that you sent to me the last week. In one of the emails, you suggested continuation of the subject that you presented last week. I think especially focusing on the issues of isocalculus, I think is what is isodifferential calculus is what you mentioned as a primary topic. I think I haven't set a particular date for that, but I did just sort of open the possibility that perhaps on October 27th we could spend some time discussing that.
Thank you, Dr. Page. I appreciate your interest for sure. Let me tell you that only a few days ago, I would have said very regrettably no. You should know that since just not to speak about personal item, but since my second Moderna vaccine, my immune system kind of collapsed, and I was hit by a rather serious infection that I never had all my life. The last one has been a very strong conjunctivitis that I had to be treated with very severe treatment, cortisone to prevent further spreading, and it was a nightmare. And anyhow, I think my condition did show my last lecture. I was supposed to cancel it, but I said I didn't feel like. I said maybe I can discuss it conceptually. But anyhow, now thanks God, I have regained. I'm no longer into the severe treatment. I have regained at least not entire vision, but what it was, my old vision. But the point is I can read the formula. So I can see the mistakes that the last time I just couldn't. I just, I will not physically, my eyes as well as physical. So yes, I will be delighted, especially isodifferential calculus is crucial. The worldwide expert in isodifferential calculus is Professor Georgiev of Sorbonne University in Paris. He works often for the US Air Force, believe it or not, and is captured for several months at a time, during which, when he works for the Air Force, he's untouchable. So I don't know. I haven't heard from him from a few last week. But in the event, you are a really sophisticated mathematician. I'm not. So in the event you want a sophisticated presentation of the isodifferential calculus, I think Professor Georgiev is the best worldwide. He wrote not 1, 2, 3, 6 monographs on the isodifferential calculus. Is a monumental work published in USA by Nova. Now, what I can present is what was my main objective, give you, first of all, the physical motivation for new math. Why? For what reason? And secondly, and give you the rudimentary derivation of the calculus. And then after that, I would like to at least I would like to present some application, so at least you can see the series of fundamental problem in physics. And I have two that I would like to recommend if you approve it, of course. So there will be a 3-part presentation, each 15 minutes. First 15 minutes, origin, construction, and other collateral. Number 2, I would like to recommend as physical application. I have to remind that we're talking about iso differential, which is sos topos, preservation of the topology. So, so isodifferential is only applicable to reversible, to systems that are invariant on the time reversal, namely closed isolated systems, such as nuclear structure, molecular structure, and things like that. It's not applicable, in my view, to energy releasing processes, which we need a broader admissible approach. So the first I will suggest, if you approve, to see how how we derive the characteristics of the deuteron, and particularly for the century-old controversy regarding the representation of spin 1 of the deuteron, that according to quantum mechanics should have spin 0, because the only stable coupling of a proton and electron spin 1/2 is the singlet spin 0. To avoid that, then colleagues, as you know, they assume that the deuteron is in a combination of orbital states. What's total angular momentum is 1. This was my time at MIT. I had to contain myself, with an extreme, for respect of my colleagues, and I did contain myself, but I could not accept it. The deuteron, with all due respect, infinite respect, the deuteron in isolated, when isolated, is in the ground state. This is evident. So we have to represent the spin 1 in the ground state. If the mathematics of quantum mechanics cannot do that, then we have to look for new mathematics. That's the very, very essence of the issue. And then the third one, if you are interested, I would like to touch the very important question that I had the other meeting, and regarding I mentioned the application to the first achievement of an attractive force between identical valence electrons that in the physical reality have an enormous repulsive force in the range of hundreds of newtons. If that will be maybe of interest to you, also because proves the last statement of the EPR argument, and also because may give you the elements to show that apparently, in our opinion, isomathematics and isomechanics appears to eliminate the quantum mechanical divergency, which are now object of a major worldwide controversy, beginning from quantum electrodynamics. That's Dirac view, that the numbers of quantum electrodynamics are unacceptable because you cannot subtract an infinity with another infinity and then extract number. That was the Dirac view. I share that view. So the point is, what we have done, there was no other way. My God, the Feynman, his history, etc., etc. But the point is, this is magnificent what has been done, the best they could possibly do. But we cannot stop there. This is the whole point. So we cannot stop there and see whether we can. That's essentially it. What I suggest.
Well, I think that's really good. I would just before I introduce Dr. Grzegorz. Is the name different?
Hello, everybody. Sorry for my nick, but it's login for Google. My true name is Grzegorz Marcin Koczan. So sorry for this.
Okay, it just seemed, I said, it's you, but different last name, apparently. So just before you showed up,
can I start?
Just a few minutes. I just wanted to just summarize our discussion from a bit earlier. Just before you showed up, I was advertising for the possibility of continuation of discussion or on various topics on October 27th, where we don't currently have any particular scheduled speaker. So that, of course, would include continuations of questions from your talk today, Grzegorz. And that's about it. So some of the people here, I'm sure, would remember Dr. Can I practice saying your name, your last name again?
Koczan.
Koczan, yes.
Koczan.
Koczan. Okay, Dr. Koczan. Anyway, gave a presentation during our GOL seminar at the end of August, and I'm sure everyone recognizes his name from that. This work, as I understand it, is a continuation in some sense of the same subject, and it intersects considerably with the research of Dr. Ushevich, from Zbigniew Ushevich, on the subject of relativity. So although there are differences in approach and in some methodologies, I know that they did exchange extensive emails on the subject, and I think that it'll be very interesting to hear what Grzegorz has to say. So, Dr. Koczek?
Koczan.
Koczan. I'm sorry for my pronunciation.
Can I share? And
Yes,
you can see this
Yes,
my name on.
Yes, you are currently sharing your screen.
But
see.
I can't sharing. Why?
No, it is.
I see.
We see your screen.
You see. So sorry. Okay,
yes,
I understand.
Yes,
Okay, it's my name. Yes, Grzegorz Koczan.
Yes. Okay, so please continue, and keep in mind this is an informal presentation and discussion. So, on the other hand, please indicate whether you would like questions during your talk or to wait to the end. Some speakers have different preferences. What is your preference?
Doesn't matter. Please ask.
Okay.
Can I start?
Please continue. Please start.
Okay. Hello, everyone. Thank you to the organizers, Bill Page and Jesus Cruz Guzman, for inviting me to the meeting. My name is Grzegorz Koczan, and I was present on GOL 2021. Today, I will discuss the poster which I presented at the 47th Congress of Polish Physicists. The poster was in Polish, but I have prepared an English version for today's meeting. The title of this poster is the linear geometrical construction of the correspondence of 4D and 3D vector in special relativity containing covariant ternary relativistic acceleration. It is simply a geometric drawing relationship between 4 vector and 3 vector for momentum, position, velocity, force, and acceleration. The most important things here is the acceleration, the relation of which is the most difficult. Its addition, it was able to define some new kind of relativistic acceleration, intermediate between the force acceleration, and the ordinary free acceleration. In correspondence with Professor Osiewicz, Professor Osiewicz supported this newly defined acceleration and called it my surname. At GOL 2021, I did not talk about acceleration, but I only talk about relative velocity, not acceleration on the GOL. On the acceleration, I talk today. Let's see. Where is my mouse? I see. Okay. let's see abstract. In the previous Congress, 26, I presented another poster when I defined, actually I show new definition of acceleration. I published this firstly in Acta Physica Polonica, and secondly in Result in Physics. That's why on the next Congress, I decided present these concepts more easy, more simple in geometrical way. Let's go. Let's see this table. This is table correspondence, three-dimensional vector and four-dimensional vector. I ask, could you see my arrow mouse? You see?
Yes.
Arrow? Okay,
Yes,
thank you.
We can see where you're pointing, yes.
Thank you very much. For example, position, this is three vector, and for position is four vector, zero the component is c plus times time, and free vector. Next, velocity, free vector, and velocity four vector. We see that spatial component of four vector is not the same. It's not free vector exactly, but is multiplied by gamma factor. That's why it's rank 1.
Is that superscript, the superscript on gamma? What does it refer to?
Gamma to power 1, yes. Super,
So
yes.
It's just gamma.
Yes, it's just, of course, gamma. It's this one, it's to understand that rank is 2. It's explained. Next, for example, momentum is 0 rank, how position. Force rank 1, how velocity. What about acceleration? Acceleration, we see here is rank 2 in this case, but it's not so easy. Let's go to my publication in Result in Physics, this extended table. In here we see that part, three-dimensional part of four position, a vector, it's more complicated if we used ordinary acceleration. This bold A is ordinary acceleration, but this capital A is special acceleration. It's my acceleration. It's I called it relativistic acceleration or ternary acceleration because it's based on inter alia, based on Osiewicz ternary velocity. Let's go to quantities.
Can I just ask for explanation of the definition of rank?
Okay, of course. Definition is simple. It's a power. It's a power. If we, for example, for acceleration, we compare comparison three-dimensional acceleration and three-dimensional part of for acceleration, and gamma power is defined rank of quantity, physical quantity. Okay, it's clear.
So it's the order of gamma.
Yeah. Yes, order of gamma. Okay, of course. Gamma 2 to 1 is rank 1. Gamma 2 rank 2. Gamma 0 rank 0. Gamma -1 is rank -1. For example, relativistic mass. Its relativistic mass is very big problem. It's my article in Result in Physics. I have done 10 definition of relativistic mass, but it's problem, controversial problem. It's not for today. Let's go.
Okay, just one further comment then. You assume that gamma enters only as a multiplicative scalar, I guess.
Yes, yes, mass is here from scalar and pseudoscalar and quasi-scalar, but rest quantities is vector in this table. Okay.
So how does your definition of acceleration differ from the usual definition of acceleration in special?
Yes, the definition of new acceleration in this table. This is a simplest formula for this definition. It used gamma in top and bottom gamma, but it's a simplest formula. It's not definition. Definition I used, for example, here equation 63. It's normal derivation according to time, but we use tutaj subsection ternary relative velocity to in this operation. It's not ordinary subsection. Subsection it's ordinary to ternary way. Okay. It's I know its acceleration is very important, very interesting, but title of this today poster is not concentrate on acceleration, but on the definition. I want to see construct geometrical. Yes. Firstly, let's see. Let's see quantities rank 0, momentum and position. It's more. It's easiest way. This is for momentum, and we project this for momentum on free space to its orthogonal projection. It's very simple. everything is understood, I think, in this project. Nothing special. We only know about it for velocity of reference frame. Sigma mu is for velocity of reference frame, and free dimensional free space is orthogonal to sigma mu. And that's it, if we must to know. Let's go. Now we have for position green vector x mu. Firstly, simplest projection, orthogonal projection, it's give here r vector, the same for momentum, but exist different way to project for momentum. For example, we can project for position used for velocity, epsilon mu. It's for velocity of material points. What is doesn't mean? We get q vector. Q vector we can call retarded position of this material point in, for example, in zero time. Yes, because for position have no general not zero time. Yes, but if we want to show where was material point, we need this way projection. There is conclusion. There is two-way projection: orthogonal projection or projection. What is in English? Projection. Skew projection. No, not orthogonal, but skew projection with velocity direction.
Grzegorz, could you explain this notion of retarded from the point of view, more operational point of view? Are you referring here to?
Because retarded or advanced. For example, if green vector is upper, then the vector q is retarded. When green vector is low, that q is advanced. It's we must comparison zero component of for position c time. If time is over zero, that's q is retarded, and time less than zero, that means q is advanced. It's a geometrical trick. On this picture, exactly is this position is retarded because time it's flow up. Okay. Sorry for my language.
Yeah, I have
No,
one question or comment.
Please.
How would your way of looking at things relate to Minkowski space-time? This is really a takeoff of the Pauli algebra. It would looks like. Is there any relation? Can you put this in Minkowski space-time?
Yes, it's Minkowski space-time. Yes.
Oh, okay, so I see. Yeah, I'm thinking.
Yes, of course, it's four-dimensional Minkowski space-time. I use signature plus, minus, minus, minus.
Okay.
I
was just thinking about relationship to Hessne's formalism of special relativity, where he uses a Dirac vector, a vector in space becomes a Dirac bivector in space-time, in Minkowski space-time, whereas it looks very similar to what you're doing with your projections, except you project the Minkowski vector by the inertia, the gamma zero of the inertial frame into the Minkowski vector, position vector X, to get the CT, and then the space-like vector X is the ordinary position vector in space-time as the even subalgebra of the Dirac algebra. So I don't know if you've related or seen Hessne's work on special relativity, the relationship between the Pauli and the Dirac algebra is the even subalgebra of the Minkowski signature plus 1 minus 1 minus 1 minus 1 as you have it.
Okay, it was comment only, tak? No, not question. Okay.
Well, yeah, I'm just wondering whether your formalism is really the same as Hessne's point of view.
Hessian.
Where the Pauli algebra.
Yes, but it was start. I am start, and the most important result in the second pillar. In the first pillar, it's very, very simple, but first pillar is not trivial.
Okay, well, go ahead.
Let's go to quantities rank 1, or somebody want to ask? Professor Santilli, what?
Yes, I believe your formula for the velocity and the acceleration is very interesting indeed, and I'm familiar with that. Oh, of course, I'm familiar, of course, with Professor Odziewicz's view, but I was not aware of your formulation. Starting at the Newtonian level, Newton admitted velocity-dependent forces, but it's unknown to my knowledge whether he admitted acceleration forces. So just to indicate that acceleration-dependent acceleration, is a very intriguing field of field that I'm very interested. Now, passing at the level of Minkowski, I think your formulation is correct. Again, not to repeat, but I'm interested in your view regarding the compatibility of the acceleration-dependent forces with special relativity, which is an intriguing problem in my view. I appreciate your view.
I don't understand a question.
Well, special relativity can be the axiom of special relativity can be defined from an inertial reference frame. Of course. And generally the acceleration-dependent forces are not considered part in general. That's why the issue is intriguing, very intriguing in my view. So how do formulate the compatibility of acceleration-dependent forces with special relativity? This is the issue.
Inertial frame, special relativity is defined in inertial frame, yes? If you ask about no inertial frame, it's ask about general relativity, I mean, yes?
That was indeed that you are anticipating my next question. So in other words, because the introduction of introduction of acceleration dependent force may not necessarily, but may create problem in the definition of the axiom of special relativity. However, part of my question was, is this an acceleration with respect to the observer in an inertial frame, or it is a relative acceleration between two particles? Because in the second case, maybe there are ways to render acceleration forces compatible with the axiom. Because if it is a relative acceleration between two particles, their center of mass will be at rest with respect to the observer, and so special relativity will occur without going, as you correctly stated, to pass to general relativity. So the problem is very intriguing because it's related to the actual explicit form of the interaction. For instance, Professor Cruz is working now on the axiomatic formulation of interaction, and some of the realization may be precisely acceleration dependent, in which case your definition of the acceleration forces will be squarely into the picture.
Okay, thank you for comments and questions. And let's go to quantities rank 2, velocity and force. We see here green vector is for velocity. We must project this for velocity on free space, but we can scale this gamma factor. It is impossible this construct. It's a simple construct when sigma mu is for velocity of a reference frame, and we drawn red vector orthogonal to reference frame for velocity, and go to green vector for velocity of particle. And then we get green vector. Green vector is exactly Osiewicz-Bolus binary velocity. Next, we project trivial projects on free space. Let's go to force. Force is a little more difficult because for example, for force is a space-like vector, but we can use previous construct and Thales theorem, and for use this parallel lines, we can scale gamma factor scale for velocity to for force gamma factor, and then we can orthogonal project P point to R point, and we get yellow free vector of forces. It is construct. It's a less more complicated, but it's not very complicated. I hope that it's understand. It's my language is only not clear, but I hope drawing is more clear than my language. it's here not very problem. Any one problem, but I don't.
Review the meaning. Can we review the meaning of some of the symbols here in this diagram?
Yes.
Let me ask about a few different symbols. So you have the sigma. This is the
for velocity of reference frame. For vector reference frame. Epsilon mu
so
green.
This is we should think of this as the velocity of the observer or something like this, right?
Yes, sigma observer. Yes, epsilon green vector is velocity of material point. Omega mu is
velocity of the material point.
Relative binary relative velocity in this reference frame. Yes, omega mu is its position in free space. Yes.
Usually that's denoted by a gamma vector or a Dirac vector. A four vector is a Dirac vector, right? Usually denoted by gamma 0, gamma 1, gamma 2, gamma 3. Rather than sigmas usually represent polyvectors. That's the way I understand it, at least.
Sigma reference frame vector. Understand. Small f is 4 force, and capital F vector is 3 force. I use here two notation. Exactly 3 force is notation with vector. It's free vector in vector who have three components, and it is lie in free space. And next notation, F capital mu, it's the same vector, yellow vector, but it is formally 4 vector which have 0 component is 0. Time component is 0. It's formal. I show over here. Tutaj F few mu is 4 vector 0 fx fy fz, but f3 vector on with vector on the top, it's free vector only without 0 on the beginning. It's something this, okay? Okay, let's go to third pillar, quantity rank 2, acceleration. It's more difficult. Okay. Tutaj what is color? Violet vector alpha mu is the 4 vector of acceleration. Is 4 acceleration. We project this 4 acceleration two way. Orthogonal project L L project to M. It's orthogonal projection. Okay. Second projection is along for velocity. This projection L point go to N point. Yes, that's why we have two projection. For example, vector Km, it's orthogonal projection of for velocity, and second vector Kn, it's Kn. It's orthogonal. It's no orthogonal. It's skew projection along velocity. Okay, it's these projections is first step to this construct. Second step, we need to scale this projection vector to gamma square times, because acceleration is have rank 2. We need scaling gamma square times. It's turned out that it's so easy. We can do it for one how tell ON, it is a segment. We need one segment, and that's it. Segment NO is orthogonal to MN segment. It's MNO, it's right angle. It's more important angle on this diagram. When we draw segment NO, we have white vector capital A on arrow. This white vector is relativistic. Relativistic acceleration is original acceleration. This, but ordinary acceleration is small capital, and we make another step. For example, third step to construct it, but it's so simple. Segment OP is parallel to segment MN. When we done P point, and we construct ordinary acceleration A, small a. Yes. In here, this flat, the same construct on the flat position. It's I think that it's this section is important. It is noteworthy that the relativistic acceleration KO, denoted by capital letters A with an arrow, requires fewer design steps than the ordinary acceleration denoted by a lowercase letter in with arrow. Moreover, it's very important. Moreover, for the acceleration parallel to velocity in the 3D sense, point zero consists with a point n. This 0 and n is the one point. So the relativistic acceleration KO is then a direct oblique projection along the for velocity. In other words, in case parallel vector to construct relativistic ternary acceleration, we need only one step: oblique skew projection. Nothing else. Only one move, and we have this acceleration. But for construct ordinary acceleration, we need combination based Thales theorem. It's a problem, but ternary acceleration is one cut and everything. That's it. We can finally formally write this vector free vector for formulation for vectors formulation. I call it covariant equation. Yes, it's we see here. It's something similar, but ordinary acceleration, this second equation, is more complicated. For example, in second part of this equation is, I think, a little complicated because denominator is free rank here. Conclusion: the geometric 4D to 3D construction correspondence of 6 mechanical vector quantities turned out to be simpler than expected. Assuming the knowledge of the 4-velocity reference system and 3-velocity of the described body and the position retarded to the time construction, the constructions are reversible so that 4D to 3D and another 3D to 4D correspondence is mutually ambiguous. On the other hand, the construction of ternary relativistic acceleration turned out to be based on the specific orthogonal cutoff defined on pair projection, orthogonal and oblique along the 4D velocity. Thank you for attention, and please ask question in simple language. Thank you.
My first question would be related to the conclusion. Are you saying that in the case of acceleration, you don't see that the constructions are not reversible in the sense that you defined it for velocities? So you're suggesting that there is a difference, an irreducible difference between acceleration defined in the 3D sense and the acceleration defined in the 4D sense. Is that?
I understand this problem. That's project vector have information about, must information about velocity. We need velocity information to define, for example, retarded position. We must, for example, let's see project for force. This project use information about velocity. Free force use information about velocity, and about acceleration too. It's need language, three-dimensional language needs information about several vectors, but it's equivalent correspondence formulation. For the we have defined physics in language for the language, and full equivalently, and for the language. Nothing. Nobody claim. Somebody claimed that it's only one system. It's good, but nothing. Nobody prove it. I think.
Okay. Does anybody else have a question?
I have a comment.
Garrett, your microphone is off.
Okay. May I have a comment?
Garrett is speaking, but his microphone is off.
Yeah, okay. Yeah, I would like to give a talk and show how some of these ideas, I think, of Professor Koczan are related to Hesny's idea of interpreting space-like vectors as bivectors in the Dirac algebra of space-time. I think it separates the ideas in a very nice way, and I think it must be very closely related to these ideas of Professor Koczan.
Hessian, what Hessian?
Hesny's, HES. I can send you a reference to Space-Time Algebra, his most well-known book about special relativity, and I might even have I don't have a copy right here, but
okay. No.
yeah,
Please,
the Dirac algebra has signature +1, -1, -1, -1, and the Pauli algebra of bivectors, which the even subalgebra of the Dirac algebra, have signature +, and are anti-commutative. And in the geometric algebra of space-time, Hesny's calls the Dirac algebra space-time algebra, whereas the Pauli algebra is just each inertial frame consists of a distinct subset of bivectors of the overall invariant Dirac algebra of space-time. So it distinguishes clearly between, as a projection, really, which is exactly what you're doing, it looks like to me.
Yes, but I don't, today I don't talk about tensors and about bivector. I talk about vector, only vector. It's the simplest.
Well, a Dirac vector is different than a Dirac 4 vector is different than a Pauli 3 vector, but they are related, closely related to each other.
There are, what is a Dirac vector? What is it?
Okay.
Dirac vector.
So the Dirac algebra is a Clifford algebra generated by 4 vectors, the gamma vectors, gamma 0, gamma 1, gamma 2, gamma 3. Gamma 0 squared equals +1, gamma 1 and gamma 2 squared, gamma 3 squared is equal to -1. But if you take the bivectors, the gamma 0 times gamma 1, say, then that
Gamma Dirac, you talk about gamma Dirac?
yeah.
No. Well, he means, yes, using
Dirac
the gamma matrices
Yeah,
as basis of a vector.
It's complicated. It's
No,
complicated.
it's not really
No,
complicated.
no,
Really,
I don't agree.
well, that's why I like to get to talk
Language,
about it. I think
language,
it's pretty simple,
gamma
really.
Dirac, gamma Dirac language and formalis of Dirac is very. I know this formalis, of course, not problem, but I want understand everything very deeper, very deep understand in very simple way. On I don't know human. I don't know any physics, any mathematics who understand the full formalis of Dirac. Full. I don't. It's a lot of books, of course, but it's complicated formalis. Anybody don't understand it quite. But I don't. For me, I don't understand. I don't want. I am don't interesting things which I can't understand fully. Fully, I won't understand. I can understand only very simple structure. Today, we see simple structure, vector. If you talk about more complicated vector, no problem. But you can see in this more difficult problem, you can see K.
Yeah, but you talk about a 3 vector and a 4 vector. A vector is a vector, period. You know, not necessarily.
Of course, it's terminology. Yes, it's notation terminology.
Yeah, in one case, your vector has a scalar component and 3 vector components, let's say. Whereas in the other case, it's just, you know, anyway. So I think this idea of the even subalgebra of the Dirac algebra being the polyalgebra really simplifies ideas rather than making it. Is your training as a mathematician or as a physicist? Are you
I'm a theoretical physicist.
Okay.
I know the direct formalis and Clifford algebra a little, but Clifford algebra, it's not physical for me.
Oh, I think it's very physical. So I would like to give a talk showing how.
Okay, but not exactly physical. Not exactly physical. It's I think.
I would like to explain how it is physical. I believe it is physical, really. So, but again,
well,
has a different point of view.
On this same point, Grzegorz, would you claim that the language that you use in terms of vectors is sufficient, like in itself? Like, for example, an argument might be made that a bivector cannot be fully described as in terms of 2 vectors. So for example, you can't always say that a bivector is a product in Clifford sense.
For example, bivector is the multiply to 1 vector. Yes, it's A mu B nu minus A nu B mu. That's it. Yes, everything about it.
A bivector is a directed plane segment, just as a vector is a directed line segment.
But
a plane segment.
Let me give you another. Well, I have another simple way. Let me give you another bivector. Suppose we do the exterior derivative of a vector. So the exterior
derivative?
derivative is going to be exterior derivative, yes. So we take the, just write like dA, right? Where D is the exterior derivative of A.
D, it's differential of
Exterior differential.
Well, that's like differential forms then, I guess you're talking about differential forms.
Yes,
differential
yes,
forms.
yes, okay. Yeah, I'm sorry, we should be talking about forms rather than vectors, but.
Let's go form omega form, for example. Omega
Yes.
mu dx mu. Yes, it's one form. It's only contravariant vector. Yes, it's
Okay.
equivalent. It's the tensor with lower index.
Sure, but the exterior derivative of this is a biform, is a two form.
External derivative, of course. Something is
Okay. How can I express it? No, I'm not quite expressing what I need to express properly. Consider rotations in 4 dimensions. Right? So some rotations in 4 dimensions can be described in terms of 2 vectors. So that what's the right way to do this? What I'm talking about are what referred to as double rotations in 4-dimensional space. So such double rotations are not described in terms of a pair of reflections. They are irreducibly described by a bivector, or more properly, like Hessenese does this quite a bit.
The best way to parameterize rotation is a Rodriguez vector. Is the best.
Is a what?
Rodriguez vector.
Oh, Rodriguez. Well, I think of a rotation as always taking place in the plane. And of course, every dimension has more combination of entries taken two at a time.
Rotation 1 and rotation 2 leads to rotation 3. Yes, it's not problem. But we have problem rotation and boost, Laurent boost. It's yes, okay, but I don't talk about it, but I boost and boost, Lorentz and Lorentz, yes. Lorentz, one boost Lorentz and second boost Lorentz, we have problem, yes. It's general, not Lorentz boost, yes. It's general problem to meaning of relative velocity, acceleration, and
consists of a boost and a rotation. Yeah, I think,
Yes, yes, yes.
But Garrett, isn't it correct that in Heston's formalism, the relative velocity is a bivector?
yes, relative velocity.
Yeah.
Well, that's just an ordinary velocity is a bivector in space time. An inertial frame is determined by
Which I ask which relative velocity.
Well, that's right. Relative velocity with respect to an observer. Each rest frame is defined by a constant gamma vector, gamma zero. The time, the vector in the Dirac algebra, which has square one. The space-like vectors in the Dirac algebra are square minus one.
Body A, body B, and observer. Yes, observer.
So think of an observer as corresponding to gamma zero. That's a Dirac vector in the Dirac algebra. Now you take gamma one times gamma zero, that's a quantity that behaves as the direction of the x-axis. Well, you can think about it. In relativity, if you take a vector and you sweep it out in a direction, it's defining a bivector, okay? Sweep it out like this, it's defining a plane, and that's the plane of this that defines the second inertial system. Anyway, I like to talk about these ideas. I could.
Maybe it's true because Osiewicz defined two kinds of relative velocity: binary velocity and ternary velocity. Ternary velocity depends on three vector: observer vector, first body vector, and second body vector.
Okay, so this is where the idea Bishop come involved, where he talks about that's the groupoid ideas, and that's a little more. I'd like to understand that better myself. I don't quite understand exactly what the difference between Auger's viewpoint of, when he points out that the multiplying is not really associative. That was his criticism of the standard way of looking at the Lorentz algebra as an associative algebra. So that would be where Professor Page's ideas.
Well, yeah, it's the composition of three velocities that is not associative.
Yes,
Yeah,
we
there was
have problem with no associative.
Yes, if I may have a comment, this very interesting discussions, I think could be focused better if we could consider a specific case in which I do see the emergence of acceleration-dependent forces. That's the reason I'm interested in your talk. But in whether there are centripetal forces, namely I'm referring to the relativistic two-body bound state, such as, for instance, we expect to be the mesons to be the they claim particle, anti-particle, the quark, anti-quark, or whatever. But there seems to be evidence that for instance, kaon is stable because of an internal centripetal acceleration-dependent force. The internal force that depends on the acceleration. And I believe your lecture could be applied specifically to a model like this, because there is open in this case, since the centripetal the acceleration is relative to the two constituents, there seems to be a way of avoiding the transition to gravitation, just remaining at the level of special relativity, because the observer remains in an inertial state. And maintaining special relativity will help a lot to calculations substantially, apart from historical viewpoint. So the issue is whether the tangential speed it can be formulated not only according to your view, but also according to a standard formulation by a vector. If that's the case, then of course the same will be for the acceleration. Although in principle, my personal view is that whenever there are axiomatic formulations, such as the vector as can be expressed with certain axiom, and then axiom admit a variety of realization. This is generally my view and personal experience. So the point of the discussion, I believe, in principle, there should be a connection indeed, because all formulation I heard, they verify the same axiom, except the violation of the case of which associativity is violating, then it's a totally different. I don't know whether I made sense, but if it will apply to a specific case, I think it will help to resolve this important discussion, which I do believe has important implication in actual real physical model. Yes, it's my view.
Okay.
Greg, as what you wrote here is, say, the relativistic dynamics in, say, the equation that you wrote there for force, right? F equals ma effectively presumes that the force is proportional to that derivative of velocity. But Dr. Santilli is referring to the situation where the dynamics is more complicated.
Yes, it's a centripetal force. It's different than, yes, it is different. But it's the only system.
The dynamics could, so in a sense, you separate the notion of force from acceleration in some nonlinear way.
But there will be nonlinear theory, that's true. But it's the only state, the only physical system that I know in which the acceleration, the centripetal forces, which are acceleration dependent, seems to be unavoidable without the. So
but there is one velocity, one body velocity. We have a lot of forces, but velocity of the body is one. Yes, it's not problem. Velocity body, it's not a problem.
Yes.
F1, F2, F3, not problem for this formulation.
I think it should be applicable. Yes, I agree. It should be applicable specifically to a relativistic bound state of two particles. Yeah. And it will help to clarify the dynamics of those bound states, because in my view are still unknown. Well, the equation of the structural equation of a kaon as being composed by a quark and an antiquark, I've never seen it. Maybe I will die before seeing it, but that's another story. It's okay. See, Dr. Page and Dr. Garrett, this is related to what we discussed before. In order how to achieve the physics, there are fundamental physical problems. Open. We just touched one before, just before our speech. Between the two identical electrons in a valence bond that they repel each other with a monstrous Coulomb force, there are hundreds of newtons. So the only way is to extract some, well, there are a number of ways. It's based on EPR entanglement, but one of the ways, from a dynamical viewpoint connected with our speaker, the whole thing seems to be centered in identifying a suitable centripetal force. And then we look at the physical origin of that physical force and how it overcomes this horrendous repulsion. So
yeah, I'm very interested in how your ISO calculus fits in with the ordinary calculus. Maybe that would also help understand some of these ideas in the more general sense.
Thank you. I'm really touched. I'm glad my eyes are back to partial normality, or at least I can check the equations when we discuss it next time. Thank you. Appreciate it.
I think I have maybe one more question that I could try to ask Greg as. Let me return. Yeah, can you show the if you scroll it towards the top of your poster, but in this same column, third column. Yes, this diagram is good. The acceleration one. Yes. Now, I'd like to understand in which sense the acceleration is space-like. So if we have a force applied to a body, then
we talk about velocity or acceleration?
Acceleration.
Acceleration. Fig 5, yes? Please.
Yes.
Okay.
So you were referring to the acceleration as being perpendicular to the velocity of the body?
Yes, in 3D meaning, we need 3D vectors. We have one way. It 3D vectors needs orthogonal for velocity. We haven't second way. It's one way in 3D language. I can see any different way.
But here on this diagram, you show only the 4 velocity, right? You don't show the 3 velocity on this diagram.
Yes, because it's not too need for this construction.
Maybe let me. I think I can. Yes, let me try. So this, if I'm talking maybe about this vector. This is the projection of you have this 4 velocity, and you are projecting it into 3 space. So
yes, but it is not velocity. It's not velocity. It's something like acceleration.
Isn't it the same as this? Or
if I see here, it's for example, a capital A gamma square or alpha vector. It's three-dimensional part of 4 vector. It's m km and this n a ordinary acceleration gamma square. That's why this vector is something delta something a, yes, in meter secunda square. It's not velocity. It's something like acceleration. Okay.
Well, I still trying to understand this this part of your diagram here, right? Like this. So this, you have this is a 4 velocity, right?
Yes, yes. This direction or for velocity, but only direction, not length on the direction, not length of velocity. It's on the direction. Yes. If I have a pen, it's I have direction, but I don't know. It's 10 centimeter, 12 centimeter. That doesn't matter. Centimeters, it doesn't matter, because the velocity is different units, different units. It's
okay.
The problem I have with the picture is that sigma mu is in a different, is a 4 vector, whereas acceleration is a 3 vector in the same picture. So you have 2 different kinds of vectors in the same picture.
I don't understand. Sigma mu is for force of reference frame. 4 vector of reference frame, and okay.
The plane consists of only 3 vectors, whereas sigma mu, well, there's 4 basis vectors, 0, 1, 2, and 3. Whereas with in the plane you only have three vectors. So you're
which 3 vector?
Okay, your capital A is acceleration. That's a 3 vector. Whereas gamma mu, that's a 4 vector, and there are 4 of those. And A, of course, is
but here we don't see gamma vector. Yes, you talk about gamma, which we don't see. Yes, I understand you.
But Garrett, this is for
sigma. The sigma vectors are your 4 vectors. I'm sorry. The
it's alpha. No, not sigma.
Like sigma you have pointing straight up.
Sigma, this. Yes.
That's a 4 vector.
Yes.
Right.
Yes.
And
4 vector.
Alpha
acceleration
also
is a 3 vector.
This acceleration is 3 vector, but this acceleration it's 4 vector.
So in the same diagram, you have a 4 vector sigma mu and a 3 vector acceleration, capital A. That's a 3 vector. So you have a 4 vector. So that's a seven-dimensional space we're talking about then, is it not?
No, I don't think it's that complicated, Garrett. Like both alpha and sigma are 4 vectors. Right? So
yes, of course.
They point out of the plane, right? But Grzegorz has this plane which represents 3-dimensional space, right? So it's this 3-dimensional space is the kernel of this 4 vector, right? It's all of the 4-dimensional space that is orthogonal to sigma. So,
yes.
Right. So it's important that this blue area be considered to be orthogonal to sigma, right?
Of course.
And so when you write A, for example, with the vector notation, this is confined to this blue surface, if you like to call it that, to this plane, right?
Okay, so the blue plane is really the 3-dimensional plane of ordinary space, whereas anything above the plane, well, that's a mixture
of course.
Yes, that's
okay,
correct.
okay.
Yes. So but there is some overlap. Like, for example, that's why there are 2 notations for the space-like part of the acceleration also is written as A with a superscript mu. That is a vector that is a four-dimensional vector. It just happens to be confined to the space-like component, which corresponds to the plane, right? So that's why he wrote that these two notations are equivalent, even though they're in different spaces, right?
Yes, for example, for somebody it's equivalent,
Yes.
and for somebody it's not equivalent. It's a I don't word something like that.
Well, they coincide for a specific observer, right? So.
Okay, well, thank you. It's a little bit clearer now, I guess.
It's similar problem than zero. For example, 0 1 dimension, 0 2 dimension, and 0 3 dimension. Somebody claimed that 0 is 1, and another people talk it's a lot of zeros. For example, Osiewicz claim that zero velocity is infinite zero velocities, which body have own zero velocities. Yes, and he talked about groupoid, for example. I don't understand this idea, but he talked about it.
But so the sigma mu is a 4 vector. It has a scalar part and also 3 space-like parts too, right? Just as the acceleration in the plane, the blue plane, has only, it doesn't have the scalar part, but so each inertial system has a different scalar part, then it would seem.
In general, sigma mu have form. For example, but implicitly on this diagram we means about 0, no, sorry, not this 0, not here 0, 0, this four-dimensional 0, and C here. Yes.
No, three-dimensional 0. No, excuse me. Three-dimensional 0 and C. Is that you have in sigma mu, you have three-dimensional 0 and C. Oh, okay, C and three-dimensional 0. Okay, in this order.
It's convention, only convention.
Okay. But is this the blue plane there is the three-dimensional 0 that you have put it here in sigma mu.
Yes, if we means 3D plus 1D, it's you're right. But if we 1 dimension plus 3 dimension, it's a different way. Yes, it's no problem, I think.
Excuse me, if I understand this in good way, you are making projections in sigma mu and in B mu. those are the basis for your projections. In all your pictures, you are decomposing in sigma mu and b mu. That's that right or not?
I don't understand. Could you repeat?
Yes, that you are putting here like the direction of for velocity is b mu. That's right in this picture. B mu is the direction of
B mu. I can see B mu. What is B mu? View mu. Epsilon, tak, epsilon.
Okay.
Epsilon view, okay. This is it's for velocity.
Okay.
For velocity of material body.
Okay, then you are decomposing all your quantities in sigma mu and b mu and body for velocity. No?
You mean that all of the projections are defined relative to either sigma or to mu?
Yes.
Yes. L mu, L m, it's parallel to sigma.
Yes.
And Ln parallel to epsilon mu.
Yes, and this is your base for decomposing any quantity that you are showing here in your poster. Yes.
I don't understand.
For example, force, acceleration, velocity, position, momentum, all of them are constructed the projection taking these two directions like basis, sigma and body velocity.
Yes.
Okay.
Only momentum is have one.
Yes, because it's in the okay.
Because for velocity is parallel to momentum. That's why projection done zero. Yes.
Okay, I'd like to just put in a quick remark. A projection is an idempotent. So if you double project it, you get the same vector. So what is the actual idempotent how do you carry out this projection that you're talking about into the 3 space? How do you actually carry it out? You must have an idempotent or a projection. P squared is equal to P for a projection.
Sorry, but my language is too worse to understand you.
Well, an idempotent is any quantity like that. Also, of course, we're talking about in terms of your iso space. We have many idempotents that each idempotent projects you onto a different iso space, as I understand it. So, okay, each projection projects to a different space of an observer, a different 3 space. So how do you actually write your projection operator, which projects to any inertial frame rather than just a particular one observer? What's the second observer? How do you get to his frame?
If we have one observer, we have one orthogonal projection, one inertial frame, and
but now take a second observer. What's the new projection then to get to?
It is theory of relativity. We must need to Lorentz transformation or something similar transformation. Yes.
How do you actually write that projection to get you to a space frame of an observer?
But is the projection that we are
Are you
discussing?
asking?
I'm
Are you
sorry.
asking about the geometry here, right? I mean, you're saying this is a geometric construction, so there's a presumption that we understand what the geometry is, right? And we've implicitly said, or maybe even explicitly said, this is Minkowski space, right? So we have a geometry that's defined that way, and in this geometry we understand how to perform the operation of projection, right?
Yes, thank you for.
Is that correct? Garrett, I'm sorry. Garrett, your microphone is off. We missed.
Oh, okay.
We missed your
I was
statement.
saying that
Could you please
Zbyszek's
repeat?
idea is that all of physics should be algebra. So a projection operator is an algebraic operation.
Yeah.
Yes, yes, but
this is geometry.
But geometry also is algebra. Geometry also is algebra, geometric algebra.
But I think, Professor Garrett, that here we are looking on geometrical decomposition of these physical variables. Then, but the observer is the same. Is the same because the observer is sigma mu, and then we are taking here one geometrical decomposition for sigma mu only, only that, and we are taking like another reference the direction of the velocity of the body that is being observed. And then I think that here the idea of either potents for these projections are only geometrical. I understand that if, for example, we get the projection of velocity in the space in the tree space of the observer, after that we get that projection, we can apply again that projection and we get the same. And it's the same for the projection of the velocity of the body in the direction of moving of the observer. I think that there is no problem with that, but if we include another observer, then we need to include another sigma here. And get the construction
so
again.
A sigma prime of the second observer.
Yes, yeah, a sigma prime we need.
So can you can draw your sigma prime as a second with an angle with respect to sigma mu, I suppose.
Yes. I think we need to do that in this case. Mm-hmm.
I think I should be watching the time because we are going a bit past the time. Is there something that you would like to say in conclusion, Grzegorz? Final conclusion?
My or
yes.
something.
Yes. Dr. Koczan.
Maybe I talk this in current nature, current science, current physicists, mathematician, physicist claim geometrical. There is any geometrical picture. And I want draw true picture. For example, Mikołaj Kopernik in De Revolutionibus only draw any equation. Isaac Newton in Principia only draw any equation, only diagrams, only construction. In current science, current physics, for example, Garrett Sobczyk claim algebra is geometric. Maybe it's a little true, but not full true for me.
I agree with Zizek's goal of changing all of physics into algebra. Well, you can start with geometry, changing geometry into algebra.
But not historical. It's not historical point of view.
Well, geometry is, I don't, there shouldn't be geometry you can do by algebra. It's clear. I mean,
In ancient world, if ancient world, if you can't draw, you can't claim anything. But it's ancient world, Greek. It's very important, and I think it's too less, too small. These ancient ideas. Picture drawing, it's very important in physics. I claim.
Okay, but a squared plus b squared is equal to c squared. That's the algebra of a right triangle.
Yeah. Okay, I think at this point perhaps we should say thank you to the speaker, and thank you for everyone.
Thank you very much
participating.
Yeah.
And we will continue next week. I guess it'll be my turn to try to describe some of the work of Oshevich in relation. It will be in relation to this, but very different in approach. But and it will be more algebraic. That's true too. Okay, so. And also, I very much appreciate your offer, Garrett, to present something on Hestiny's point of view. And would you agree to make such a presentation? I guess it's would be on the 27th of October. Is that a reasonable proposal for you?
Okay, that would be the week after your talk then, right? That's in 2 weeks then, I guess.
That's right.
Or 3 weeks.
That would mean we'd. Yes, it would be the week, 2 weeks from today, right?
Okay, that's fine.
And so that would mean we'd sort of continue our discussion along the lines of relativity for.
Exactly.
for
Yeah, I
those
will
three
have something to
lectures.
say.
Okay.
How to turn
Okay, great.
special relativity into geometry. Algebra,
Okay,
geometric algebra.
Okay, thank you everyone for participating today, and we'll meet again next week.
Very well. Thank
Bye-bye.
you. Then bye-bye.
All right, have a nice
Bye-bye.
week, everybody. Bye.
Okay.
Bye.
Bye.
Much.
Bye.
Bye-bye.